Hello everyone, welcome to CK Math Foundations, and today we are going to talk about finite fields. So finite fields are a mathematical structure underlining the modern cryptography field. We will talk about the motivations behind it, how it's constructed, its operations, basically mathematical operations within the field. And at the end of the video, you will be very familiar how the finite fields are constructed and how to do operations in them. So computers, especially the early ones, can't accommodate fractional numbers effectively, leading to precision problems. So what I mean by that is, like, if you've been to school, if you do 3 divided by 10, you get 3.33, and this goes on till forever. But if you do the same operations in computer, for example, I have the notes here, you will get it too. If you do it in computers, you get errors after some digits, after some precision. It's not precise to the infinity, it can't be. So for example, in Python here, if you do till 60 decimals, you see it starts to give out like errors, like it's not 33333. And in cryptography, we need precision. So that's why we need to describe finite fields, and we will talk about it, how to construct one. So finite field, as the name suggests, it's a finite set of some values. So a cryptographer in early days decided, like, for the finite field there will be only whole numbers. So let me clear this quickly. So let's finite field as f, and there will be only whole numbers. And only a limited number of whole numbers, not the like arbitrarily large integers. And it should be able to perform all arithmetic operations, namely addition, subtraction, division, multiplication, exponential, logarithm, and all of that. So how is this finite field achieved basically? So you will have an integer set. In our case, we will have from 1 till 12. Think of it as like a clock, like 12, 1, 2, 3, like a clock. And we'll start with addition, subtractions. So imagine a clock. So what do you do when you have to tell, like, at 5 hours in 2? For example, current time is 2 o'clock and you want to add 5. What do? So you move the clock by 5 rounds. 1, 2, 3, 4, 5. You get 7. But imagine now you add 10 in it. What do you get? You don't say 17. You basically round it off like a normal clock. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you will get 5. So basically we did mod operation with 12. So whatever the digit is, we mod it by 12 to keep it within the field. So 17 mod 12, we got 5. And so this is same as modular operator, or you might also know it as remainder operator. So in cryptography, 0, like in real life, like in other mathematical field too, can be challenging, because 0 brings undefined behavior in real world too. So of course we know 0 is not on the clock face, but we can find it by using the properties of 0. What are the properties of 0? We know that 1 plus 0 is 1. 15 plus 0 is also 15. And minus 5 plus 0 is also minus 5. We basically know whatever we add with 0, that's the same result. So in the end we can say n plus 0 equal to n. So this is very important for us. So think, what is the number on the clock face that if you add that number to your chosen number, you will get your original number back. So I have this small application that I made. We can adjust this, like if you want to set it 7, 12, but let's keep the simple example. Let's keep it 12. So what number will represent a full revolution in a clock? It's 12. Like in this clock of 12, it's 12. So 12 operations will represent a complete circle, and that's why 12 is 0 on the clock now, because whatever you do, and if you add 12 to it, you will get back to the same position. Think of it as like a normal clock, like 12 hours have passed. So if it's 2, and if you move it 12 times, you will get back to 2. So similarly, if we do like in a clock, like 0, like which is basically 12 now. 12 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry for the bad drawing. So basically what we are doing is, if we do 2 plus 12 mod 12 mod 12, we get 2 back. So from now on, we will write 0 at the top of the clock, and now set will we choose from 0 to n minus 1. So in our case, 0 to n minus 1 will become 0 to 11. So that's the addition. Now the negatives. We call it additive inverse in the finite field. So let me clear this. So observe the behavior of negatives in real numbers. Like we all know, 1 plus minus 1 is equal to 0. Similarly, like anything 3 by 5 plus minus 3 by 5 equal to 0, and so on. We can conclude that n plus minus n equal to 0. This is our additive inverse or negative. Let me clear out the screen. So n plus negative n equal to 0. So we are looking for this in our finite field from 0 till 11 now. So therefore, negatives from a mathematical characteristic point of view can be understood as two numbers if they add up together yield 0. We will define negative as complement pairs of numbers that when they add up together, we will get 0. In this case, again, it will be 12. We'll call them additive inverse. So I prepared a table for you guys. So in each row, each number adds up to 12. So 1 plus 11 equal to 12, which, as we established before, 12 is 0. So 2 plus 10, 12, and we will do this for the whole set, like 6, 7, 8, 9, 10, 11. So it's the same. So here's an example. 3 minus 11. For 11, it's 1. We can write it as 1. It's 4. This means 3 plus minus 11 means inverse of 11. That is 4. Therefore, 4. So now we have a new number system, a finite set from 0 till 11. We do addition using modular arithmetic. The additive identity we establish, which is 12, basically zero element, we call it. The additive inverse, which we call replacing negatives. Okay, so now you might think, how should we do the division? So division is a bit tricky. We will cover that in the next lecture. We will start with multiplication first. So multiplication, it's not as simple as modular arithmetic. We can't just multiply and do the mod. For example, 7 times 2 equal to 14, mod 12 equal to 2. Oops. This will not work. We will take an example. I will explain it through an example. So take the example of 3. So 3 times 1 equal to 3. So I'm writing the numbers. Like, to help you visualize this better, I have prepared this small application. Oh no, just this. Yeah. So so we know that if we start at 3, so 3 times 1 is 3. So, and then we do the next, 3 times 2 is 6. So if we move, we all know that multiplication is basically addition, just n number of times. So we will add 3 to it. 1, 2, 3, we will reach 6. And then 9, 1, 2, 3. And then if we add 3 again, we will get 12, which is basically 0. And now if we do 3 times 4, so we already established this. Oh, we got 0 for 3 times 4. Yep, like here. And if we do 3 again, 1, 2, 3, we are back on 3. So 3 times 5 equal to 3 again. Then 3 times 6 will be 1, 2, 3, 6. And 3 times 7, 1, 2, 3. We are again, if you see, we are stuck in a cyclic loop. You can't get to every number from a multiple of 3. So cyclic loop or duplicity paradox, as you can see from the table. So 3 times 3 equal to 9, but 3 times 7 also equal to 9, which does not make sense, which suggests like 3 and 7 are equivalent, which is not true. And we also get absurd results like 3 times 4 equal to 0. So this makes no sense. If 3 represents a real step forward, like on the clock here, 1, 2, 3, and 4 represents a step forward, again 1, 2, 3, 4, we are somehow, when are tied together, we are getting 0. So if you move 3 and then if you move 4 times again, 4 times 3, then you are getting 0, which does not make sense. So let's try with another number in our finite field. We have from 0 to 11. Let's take the example of 5. So I'll pause the video just to write it down. So I've drawn out this table, and we'll use our clock as an example again. So 5 times 1 is 5, and if we do 5 again, 1, 2, 3, 4, 5. This should be 10. My typo. 5, 10. And if we add 5 again, 1, 2, 3, 4, 5, we get 3. So as you can see, we are not getting into a cyclic loop, and we are able to reach out to the every single element. So if we start from 5, then we were able to reach out to 1, 2, 3, 4, 5, 10, and then 3, and then 8, then 1, then 6, then 11, 4, 9, 2, 7, and 0. So as you can see, in the case of 5, it's clearly different. We can get to every number with the multiple of 5, same as in real number line system. We don't have any cyclic loop or cyclic results. We have logical results where 5 times 12 is 0. We establish 12 is 0, and anything that multiplies with 0 is 0. So in case of 3, 3 is the complete divisor of 12, which means every time you get to the top of the clock, you will get to the same point. So this is not a problem for 5, since 5 is not divisor of 12. The way to solve this problem is to make sure that none of the finite set elements share any divisors with the top number. To do that, simply pick a prime number on top of the clock instead of a number that has a lot of divisors like 12. So I have prepared this small example that you can play around with. Pick a prime number to be on the top of the clock, then every member element will behave logically under multiplication. So in this case, we are setting it as 7. We defined the prime field p equal to 7, so you have this table and you can perform the same operation with this tool, and you can play around a bit. For example, 4 times 2 give us 1, 3 times 4 give us 5, and we can reach every element in this. So there are few things that you should notice. First is the identity element. The identity element is a number. When you multiply by it, you get the same number. That's why it's called identity element, and it's 1 in real world, same as here. So anything multiplied with 1, you get back the same number. 0 is still undefined, as you can see. Anything is 0. Anything you multiply with 0 is still 0. And you also have to see the multiplicative inverse, which will become division. So any number when multiplied with the other number will give us 1, that is its multiplicative inverse. For example, for 2, the multiplicative inverse is 4. For 3, the multiplicative inverse is 5. We get 1 here. So in the table, if you see, everywhere we get 1, it's the multiplicative inverse for that number. So take this as an example. So 2 divided by 3 can be written as 2 to the power of 3 of -1, and 3 for 3 we already established the multiplicative inverse is 5, so it can be written as 2 times 5, which is 3. So 3 to the power of -1 represent multiplicative inverse. And similar to the addition case, any pair of number, if you multiply them together, you get multiplicative identity 1. Then these are called mutual multiplicative inverse. So now we have established the prime field. We have elements in it, the finite set 0, 1, 2 till p minus 1, where p is the prime number that we keep here. Then we have addition. Now we know how to do the addition. Addition is with modular arithmetic. The additive identity 0 element, so once you add with it, you get the same number. Remember the 12 in the clock example. The additive inverse, which replaces the negative, so 3 minus 11, so 3 minus 11 equal to 3 plus 1 equal to 4. So any number when they are added together, they give us 0. so that's the additive inverse of that number. For -1, it's 1. We established 11 plus 1 is 12, which is 0. That's why for 11, the additive inverse is 1. We did multiplication, and multiplication, we do multiplication with mod addition. We establish multiplicative identity, which is 1. Any number that you multiply with this, you get back the same number. The multiplicative inverse, which replaces division, like the example here we just did. And that's it for this lecture. In the next lecture, we will work on logarithms, the exponents. Thank you for watching. The code is on GitHub.